The course in general, this is the Internet Technologies and Regulation course. The idea of the entire course that will run throughout this semester is to give everyone a baseline, a good understanding of the Internet, where it came from, how it works at a technical level and at a regulatory and institutional level. And we're going to cover all of those topics. But today, the first lecture, we're going to be looking at the actual architecture of the Internet, the technologies that underlie it, and some of the various protocols and how they work and how they all fit together. In the remainder of the course, the way that we're going to run this is that there will be an hour's lecture in the morning, and then we will have a set of discussion questions. So after the first hour of the lecture, you will split off and we will have a discussion about certain topics that have been raised during the course of the lecture. For this week, there are no discussion questions. We've got a 2-hour slot for this lecture, but I very much doubt that we'll go to 2 hours. If we start to hit the 2-hour mark, then start throwing paper at me or things like that. I think that's about it. Now, in the later lectures, you will also be expected to give, in the discussion section, a short 10-minute presentation related to the topic or related to the reading list. Now, the details of that should be in the course handbook. This is very much up to you to self-organise. I'm not going to assign you weeks or topics or anything like that. You need to look into the course and the details of the course, look at the reading lists, and sort out amongst yourself in which week you're going to give presentations. I believe that there are forums and discussion places for this kind of thing for the master's students. So with that out of the way, let's get started. So in case anyone doesn't know me, I'm Joss. I will be giving some of the lectures on this course. The rest of the lectures will be given by Ian Brown. I'm a computer scientist by training, so this is why I'm covering some of the more technical stuff here. If you have any technical questions, then do feel free to try and catch me out. You probably succeed. So let's get started. The Internet architecture. So what is the Internet? What comprises the Internet? Well, the Internet is made up of millions of connected computing devices, all sorts of things. You can see them down the side there. Home PCs, not so many people have desktop PCs anymore. We've got laptops, wireless connectivity. These are generally referred to as hosts. We talk about hosts on the Internet. So a computer or a PC or a laptop or even a server, which is a more dedicated computer for running Internet applications, we tend to call them Internet hosts. And these tend to run various network applications. Now, network applications can be things like the web browser, or the email client, or they can be the web server that provides the web pages to you that you look at in your web browser. They can be the email server that handles emails for you. So apart from the hosts, apart from the computers that make up the Internet, there are the communication links themselves, the links that transfer data. We've got fibre optic links. These are made from either plastic or glass tubes, effectively, that transfer information as pulses of light. These tend to be very, very fast. They tend to sit right at the core of the Internet where we need as much speed as possible. They're seeing more and more usage towards the end user level, but for the moment it's still quite an expensive, quite a high-end technology. The traditional way to transfer information that came all the way from telegraph and the telephone systems are copper wires, the ones that you'll see running across the country wherever you go. And obviously now we're getting more and more radio and satellite transmission. Now, satellite has been around for quite a long time for international television signals and things like that. It gives you a good amount of reachability on the Internet. You can see satellites from pretty much wherever you are on the Internet, but it tends to be very costly and can incur some sort of delays in the transmission. Now, the important thing when you're talking about the links, the communication links on the Internet, probably the most important specific factor is how much data you can get down it in a given period of time, how fast the connection is. That's typically referred to as the bandwidth of the connection. So higher bandwidth, more data transferred in a given period of time, better. And so apart from the end hosts and these communication links, the key factors in the Internet are the routers. Now, routers are specialized computing devices that forward connections between computers or between networks that make up the internet, or packets of data. We'll see more about packets of data later on. So that's more of the sort of hardware level, the basic building blocks. But the way that the computers talk to each other are referred to as protocols, the internet protocols. There are a variety of internet protocols, and these determine how you say things, how a computer says things, how messages are sent, how they're received, what you do when messages are received, what you do to forward on messages. And some examples of internet protocols are TCP, or IP, or HTTP. You may get a bit fed up with the alphabet soup that comes up in these lectures. But TCP and IP are words you may well have heard. HTTP you'll see at the start of every address in your web browser. Skype is also a protocol. It's a protocol for voice transmission across the internet. Ethernet is a protocol for transmitting data across the physical wires that make up local networks in buildings like this one. So these protocols are basically a set of rules for behavior for transmitting and receiving data. And then we've got this word, internet. What does internet actually mean? Well, it's a network of networks. We tend to think of the internet as the network that's out there, the big global internet. But the word internet actually comes from a contraction of the word internetworking. It was initially conceived as a way for different networks to talk to each other, to internetwork. And eventually that was shortened down to become the internet. And so now the internet itself is made up of a lot of smaller networks. Again, we'll expand on all these topics later on. The public internet, the internet that we tend to use every day, most of us, is the public internet. It's out there. It allows global transmission of data from one side of the planet to the other. You also get private intranets. We've got one in the department. These are basically like mini versions of the internet that work within a restricted sphere. So they tend to be things that run, say, within an organization to provide local web services or calendaring services or email services. And they're almost like a closed-off version of the internet. Now, the internet being a network of networks made up of lots of computers from all around the world, we need to have a certain way that we all agree we're going to transfer information. We all need to know how to send data and where it's going to be sent. And this is where the role of internet standards come in. So standards are agreed upon rules of behavior for how things should happen on the internet. The most famous, the most important of the internet standards are what are called the RFCs, the requests for comments. These denote open standards for communicating data on the internet, how it should be done, every detail of what you should do to interoperate with other people using these same standards. And these are developed and promoted by the IETF, the Internet Engineering Task Force, which is one of the most important institutions in the development and the guidance of the internet. Now, we won't really go into the IETF and what they do today. That'll come out more in the history and development of the internet lecture. But the Internet Engineering Task Force, it's sort of worth mentioning, is made up almost entirely of engineers. Their stated goal is to make the internet work better. It's an entirely volunteer-run and volunteer-operated organisation made up from engineers around the world who come together, usually sponsored by their companies, but they come together to discuss the engineering problems of the internet and to try and make it work. So that's the view of the internet in the terms of the things that make it up, the things that comprise it. But from a service point of view, how do we use the internet? What services make up the internet? What different things do we do on the internet? The communications infrastructure of the internet allows for applications to run that we don't typically think of necessarily as distributed. But these things like the web, these are distributed applications. You have a client on your computer and it connects to a remote server to get some data and pull it back to you and to display it. If we consider that as an application in itself, then this is distributed across the entire internet. And you tend to lose just how amazing that is, that you're actually just sort of clicking on a link and you're pulling data potentially from thousands of miles away. Email, obviously, one of the first applications on the internet, often referred to as the killer internet of the application of the internet, the killer application of the internet, the thing that really initially started it going. Gaming is obviously very popular on the internet. E-commerce, banking transactions, things like that. And file sharing is obviously very important these days as well. What does the internet provide these applications? What is the medium? You know, the internet is the thing that allows all these things to happen, but what is it that really makes this this work? And this is that the internet provides a reliable way to deliver data from a source that can be anywhere on the internet to a destination that can also be anywhere on the internet. There are also ways that the internet can provide a less reliable source of data transfer, a best effort data transfer, that are used for some very specific applications. Again, we'll get into the specific applications that want best effort rather than reliable transmission later on. So protocols. Protocols are really key to the internet. They're really there at the core. They're really there at the base. Human protocols, we understand these. We have the word protocol. You know, we don't use it so much anymore, but it often referred to the way that you behave in polite society, or when you go to court in a country that has a court. Sorry, I should say court as in a monarch, the court of the king or the queen, not the court of law. These are protocols. These are ways that you behave, the right thing to say. And we've got some very simple ones, very basic ones that are less formal. Asking somebody what's the time is a standard question that is expected to receive a standard response. And I think the best example here are introductions. You know, shaking someone's hand. This is a protocol. If I walk up to somebody who I've never met before and say hello and hold out my hand like this, if they just sort of look at my hand and then look confused, then society starts to break down. We know that what you're supposed to do in a lot of Western societies is to shake the person's hand, and this is an understood protocol. So this is an agreement that we all have, that we all know about, that allow things to function. So these are the human idea of protocols. On the network, we've got very, very similar concepts, except we're obviously working with machines rather than humans. But every communication on the internet is governed by protocols, and we have the internet handshake. One of the most important steps in a TCP connection, when we connect to something over the internet, is the TCP handshake, where one computer sends a particular kind of message that is a handshake message, and the other computer responds with the responding handshake message. So these are very closely linked. These are very strong allegories here. But in general, there's specific messages that define the format, what order particular messages should come in. You don't shake someone's hand and then say hello. You tend to say hello and then shake someone's hand, this kind of thing. So just to illustrate some of these protocols in person, hello, got the time, 2 o'clock. Very easy, we all understand. And the computers are very similar in the way they do things. Can I make a TCP connection request to you? Sure, why not? Send a TCP response. Right, now we know we're talking in a TCP connection. Can you give me this web address? Sure, here it is. It really does work that simply in some senses. So that's where the internet is coming from at its base. We talk about the network, and there are certain aspects of the network. I've already talked about the core of the network, and we also have an edge to the network. Now, this is just a convenient way of talking about where things are located and how deeply embedded they are in the way that the internet infrastructure runs. The hosts, the end systems, tend to run particular applications at the edge of the network. Your PC or your laptop is not sitting in a fortified bunker somewhere handling internet connections for thousands and thousands of people. Those are the core routers that handle things for the majority of the internet. Your PC is right at the edge, sending requests effectively into the internet. You are part of the internet whenever you're connected to it, but really in the sense of your average user, you're an edge user. You're somebody sitting right at the edge of the network. So when you make a web request, you send some data into the internet handles it, it finds out where that web request should go, it goes and gets that piece of information for you, and then it handles bringing it all the way back to you, and then it pops it out to you at the edge of the network. Now, the most traditional way that this happens in the internet, or the most standard way it happens, is what's called the client-server model. And this is the same model that is used for web requests. It's the same model to some extent that's used for email requests. And the idea here is that you have a server. You have a computer that is sitting somewhere in the internet or on the internet that is always on, that is waiting to do things for the clients. This is the server. The clients are you, your web browser, your email client. And what you do is when you want to get a web page or when you want to send an email, you connect remotely from you, the client, to the server located on the internet. And the server is the thing that handles that request for you. So this is a hierarchical model to some extent. This is there's the server that is very important, and then all the clients that connect to it. Just to reiterate, a web server is probably the best example of this. Google.com's servers that sit there ready to search results for you on the internet. They are, in fact, there's more than one in the case of Google because there are so many people making requests. But effectively speaking, there is a Google.com web server, and when you want to get some information from Google.com, you, the client, connect to it and get your search results back. Now, in contrast to the client-server model, there's an alternative model, of course, called the peer-to-peer model. And the idea of the peer-to-peer model is that you remove this reliance on a centralized server and you conduct transactions between peers or clients, as you could call them, but given that there's no server, it doesn't necessarily make sense to call them clients. But peers in the network that connect to each other directly and make sort of links sideways rather than up and down a hierarchy. And this is how a lot of protocols for file sharing have often worked, partially in response to the fact that lots of people are sharing copyrighted content and they don't want the server to be taken down. So you take the server down, the system stops working. If you're in a peer-to-peer system, if somebody is sharing copyrighted content and you take down one of the peers, then you just go and get that content from some other peers. This is what drove, to some extent, the idea of peer-to-peer. So peer-to-peer is a bit more survivable, it's a bit more chaotic, it's a bit more anarchic, it's a lot of fun, but it brings in some particular problems. And we tend to see in the way that the internet develops is that there is a tendency to move in the client-server model. Because it's easier to build client-server services. It's easier to set them up and get them running. The peer-to-peer model is very good for very specific applications, but there are so many design problems, there are so many performance problems, there are so many very hard mathematical problems about how to make peer-to-peer services work that they tend to be used for very specific things. Having said that, Skype and BitTorrent are two very good examples of peer-to-peer protocols. So when you connect to somebody on Skype, you don't tend to connect through another computer. You actually are making a direct connection to that person's PC or computer on the internet. And again, BitTorrent is an example. We'll go into a little bit more detail about BitTorrent later on. So, when you're right at the end... Oh, hello?
Peer-to-peer model
Yep.
Allows for, well, that's in experimental phase at the moment, but it allows for peer-to-peer social networks to be built. Is that true that these can preserve privacy?
Wow. How long have we got? So if you're thinking about something like diaspora. Now, so the idea of something like a peer-to-peer privacy-preserving social network, which is a wonderful thing, is that when you connect to Facebook and you perform your social networking on Facebook, people talk about the privacy settings on Facebook. There are no privacy settings on Facebook because everything that is on Facebook is known by Facebook. Okay, there are privacy settings from other people, but there's no privacy from Facebook. They're the provider. In some senses, they're the medium of communication for you, so they know everything. The idea of a peer-to-peer social network is that you would store all your personal information on your computer. You would be the person that would have control of it. And if you wanted to share information or share links or share photos with other people, they could make a request to you. So you have absolute control over the sharing of your information. It's a wonderful idea. There are some limitations to it. One of the limitations in peer-to-peer is that if your PC comes off the network, if you close your laptop, you're not on that social network anymore, because anyone who tries to connect to you will find no peer, to whom to connect. So there are, like I say, this is a good example of where there are particular limitations. Facebook gives you a very always-on service. It's always there. You don't have to be connected all the time. If you want to chat with somebody or send them a message, you don't necessarily have to be connected at the same time as them. In a peer-to-peer system, their entire profile would, to some extent, drop off the network when they weren't there. Now, there are ways to get around this. You can have a sort of stub profile for them that other people store and can make available when they're not actually there to answer requests personally. So there's lots of little engineering tricks there, but whilst it's a great idea, it's not seeing a lot of sort of work in practice. And a sort of extended version of this, somewhere we can take this even further, is in making the network itself peer-to-peer. So the network I'm describing here, this network of networks, as we'll see a little bit later on, is hierarchical in its sense. You've got the edge routers on the edge of the network, and then you connect through a router to a larger network, and then that larger network will connect you up to the really big networks that make up the core of the internet. So this is all hierarchical, but you can actually create networks using what are called mesh approaches, where nobody is the key router. Everyone just connects to the other person. So if this laptop wants to send a message to that laptop, now at the moment in the system we're running here, this laptop will send a wireless signal to the router wherever it is, somewhere, and then it will go from the router back down to that computer over there.
Is that similar to BT Open Zone or BT Home Hub?
No, that's mainly a wireless network. That's mainly the same as a standard wireless network. So the way that a normal wireless network works is you have a router somewhere that handles the wireless signal, and everyone is connecting to that. Everyone here who is using the browsing Facebook or whatever you're doing is connecting to my hand, the router at the moment. And if you want to send a message, you'll relay it like this. You'll say like that and like that. What a mesh network allows you to do is to just go straight across. Right, so this can be good for preserving privacy, but there are some very difficult problems involved with that, because if this computer wants to see that computer over there, and it can't reach it directly, it has to find a way through the network. So it has to be able to say, oh, I want to go to this computer first, and to this computer first, and to this computer first. That's not too difficult in a network the size of this room, but when you're talking about a network the size of the planet, with billions of connections, how do you know from that computer the route through all the other computers in the network to get to the computer on the other side, in Australia or something like that? So there are severe scalability problems with this kind of approach. We'll touch on this a little bit later, but I won't focus very much on mesh networks today. They're very good in certain senses. There's a very big project at the moment called the Freedom Box project that is aiming to create censorship-resistant networks, where you have a little box and you can just stick it anywhere, and it's solar-powered, and it'll give you an analog to the internet that nobody can shut down. But because of practical problems with scalability, at the moment we have this routing approach where you connect up to the hierarchy to a core set of networks and then back down the hierarchy, because that allows everyone to agree on who handles the information for everyone else. So it can be quite tricky. But to sort of cover this slide, the edge systems, the home PCs, how do we connect them to the network itself? Well, we've just been discussing this really, but there are residential access networks. Your home PC in your house will have a router that you plug into the wall. And that will handle your internet connection for you. Maybe you've got cable where your cable TV signal comes in, and that can handle the internet for you. And that connects you to a local network, and that local network knows how to connect out to the rest of the internet. If you're in a university or a school or a large company, you'll have an institutional access network, often larger scale, perhaps more professionally run. But again, it's really just a scaled up version of the same model. You connect into the local network either wirelessly or through a physical cable, and then that connects you to the local network, which then sort of handles everything else for you transparently. This is very important in the internet, the idea that you don't have to know what's happening out there. You just need to connect your computer and it will work. There are also mobile networks, your mobile phone, which works slightly differently, but to some extent they're an analog to the same thing. Your mobile phone will connect to the local tower run by the service provider, which connects you to the local network, which connects you to the rest of the internet. So this is a real feature of the way these things work. Again, a very important thing in an internet connection is the bandwidth. How much data can you get from point A to point B in a certain amount of time? Is it fast enough to stream video? Is it fast enough to stream audio? Is it fast enough to download a photograph in a relatively short period of time? I remember, and I'm sure some of you remember, sort of clicking on a photograph and waiting, a few minutes for it to pop down over your phone line. Make a cup of tea or something like that. A related property, I mean, there are two properties. People often think that bandwidth is the be-all and end-all of network connections. It is not. There's a related property or a similar property called lag. And this is not just how fast can a piece of data get from point A to point B, but how long it takes. They sound very similar, but one good way of illustrating this is if you want to transmit a really big amount of data from one side of, say, the US to the other, one coast of the US to the other coast of the US. Say you're a big company and you've just backed up all your servers and you have 100 gigabytes of data to transfer. The fastest way to get that data from one side of the country to the other is to put it onto very big hard drives and drive a truck or fly a plane across the country. Now, in real terms, if that takes, say, 3 days to drive across the country, you've got a bandwidth of 100 gigabytes per 3 days, which is actually quite good. It's a good data transmission speed. It's better than you'll get on the internet. But the lag is terrible, because if you want to send one message, you've got to wait 3 days for it to get there and 3 days for it to get back. This is how lag works. So you can have a very good bandwidth, but a very poor lag. The hard drive in truck network access mechanism isn't very good for Skype because you won't get your voice communications very quickly. But it's wonderful for transmitting huge amounts of data. If, on the other hand, you can only get a few K a second, but you can get it almost instantly, then something like Skype may well work. And the final point about network access at this level, the network connections that we see for home users, is whether they're shared lines or whether they're dedicated lines. Now the difference or the similarity here is that a shared line is obviously something that a lot of different people are using at the same time. So if there is a certain amount of bandwidth available, if there's a certain amount of transmission capacity available, then you're sharing it with other people. Maybe they're downloading a file, maybe they're downloading a photo, and your bandwidth will be correspondingly lower. Maybe they're not doing anything, and your bandwidth will be much, much higher.
Sorry, just really quick, can you repeat? Lag is the time it takes to transmit data?
Yeah. So lag is the time it takes for a message to get, say, there and back on the internet. So this is why, say, satellite connections tend to be quite poor in some senses, is because even though you can probably get quite a good bandwidth, you can probably get quite a lot of data being transferred, you have to wait for the signal to go up to the satellite and back down from the satellite. And so if you're trying to play an online game where you're trying to shoot somebody in a first-person shooter or something like that, and your connection has to wait 1 second, then by the time you've seen that the other person's there, they've already shot you and run off. And you might have much better bandwidth than they've got, but your lag time was much lower. There's a very interesting case recently. If anyone's been following the Kim.com case, the Mega Upload founder, he detected that the New Zealand government was surveilling his internet connection because he was a very, very avid online gamer, and he suddenly noticed that his lag had gone up from 150 milliseconds to 850 milliseconds because they'd installed some surveillance boxes on his internet connection, and it was slowing down his internet connection while they passed through the extra connection. So this sort of stuff can actually make a difference. Particularly, I think he was like number one player on some. I can't remember which game it was, but this is a significant part of the network. Probably the most standard, certainly in this country, way of connecting to the internet from a home connection is DSL, or the digital subscriber line. The good thing about DSL, the thing that really made it popular, was that it allowed the internet to transfer with high speeds over the existing infrastructure that we already had for telephones. The copper wires that were already there, they require some upgrading, in the network to get faster and faster speeds. But this was the technology that took us from actually connecting over the phone line and sending data in the form of sounds going down the phone line to the digital electronic pulses going over the same wires. And this is when there was an explosion from a very, very poor internet connection, a photo that takes 2 minutes to download, to the more current speeds where a photo can take only 1 minute to download. My connection anyway. So this is a physical line to the telephone central office that allows people to connect to the network. And what you see is you've got your home PC that connects to your DSL handling modem, and that connects you to the standard telephone line, which can then get you through to the internet, or if you're connecting from your home phone to the telephone network. So this gives you this means that we already had an infrastructure there for fast internet connections, and there wasn't a huge outlay required to bring the internet to most people.
Sorry, why was the typical upstream and downstream rate, why has that gone down for today?
This is an up to and a typically.
Okay.
This is quoted figures as opposed to the figures that you'll actually see. And the reason these figures are actually slightly out of date. Up to 8 megabits downstream is not a current value anymore. It's probably depending on where you are. I think 20 is not an unreasonable top quoted figure. But one of the reasons why you'll typically see a lower value than this, one is you may be on a cheaper connection where they're not giving you the full amount of the data. The other one is that when you get an internet connection from a service provider, they will say up to 10 megabit per second connection. And then in smaller print somewhere in the contract, they'll tell you how many people are sharing the line. So this is called the contention ratio, how many people are contending for the same amount of bandwidth. And I think 80 to 1 is a standard contention ratio. I think 50 to 1 is quite good. That's the numbers that I remember from the top of my head. Now, obviously, 50 to 1 or 80 to 1 sounds pretty terrible, but actually not everyone is downloading all the time. And so in practice, this works out pretty well.
Excuse me. I was just wondering, it's a bit tangential, but I was just wondering why it is that we usually stick to megabits when we talk about bandwidth, whereas whenever we're actually downloading something in the browser, it's megabytes per second usually used.
I honestly can't give you a good answer. I have a feeling that there is a good answer, but I don't know off the top of my head. I mean, one thing I would say is that 1 megabits sounds a lot better than what is it, 128 megabyte. No, sorry, 1 megabit would be 128 kbps. So it sounds a lot better. On the other hand, I guess most people wouldn't know the difference between K and M, so 128 might sound better than 1, but I don't know off the top of my head. It could simply be that it's more accurate.
Right.
But I really don't know. And don't forget the fact that historical accident plays a lot of role in these things. It could just be that that's how it's always been done.
Right.
But I can't tell you. I can't tell you that one, I'm afraid. So this is the alternative model for residential access. If you are in an area that has cable, this is a lot more common in the US than the UK, and particularly in big cities. But the idea here is that your home connection gets into a local distribution zone that is designed to handle high-speed TV networks, and so you have a much faster transmission capability there. So it's very much a very similar sort of transport system to the DSL lines, except you're working over more powerful cables, more higher bandwidth cables. Within a company, within a building or an organisation, you tend to have a much faster network because you've got sort of locally installed cables using sort of newer technologies, and you're not handling such a large amount of data. So the standard for wired internet connectivity within a university or a company is called Ethernet. An Ethernet cable is what you'll plug into the wall in a building like this if you're using a wired connection. The earlier Ethernet connections were about 10 megabits per second, went up to 100 megabits per second, became common around the year 2000 mark. Nowadays, most PCs or most Macs will have a 1 gigabit Ethernet connection on the internal port, if you still have internal ports. Most of these look very thin. I guess you probably don't have Ethernet. And 10 gigabit Ethernet is out there, but it's less common. I think you'll find you have to plug something into your thin MacBooks to get. Now, the original way that this worked was that you had what was called an Ethernet hub, which was something that you all plugged into, and it sort of split the signal out to everyone. Now, the interesting thing about the way that Ethernet hubs worked was that every time anyone sent a signal, that signal was kind of repeated off to everyone else, and people just said, "Oh, that's the signal designed for me." So if I was sending a message from this PC to that PC over there, then everyone would see the message, and only that PC would say, "Oh, that's for me, I'll get that." That was the way that hubs worked originally. And if you can imagine, this is quite inefficient because there's a lot of traffic going around that's not needed. In modern systems, there's the approach uses what's called a switch, which actually creates a direct connection between the PCs. It actually doesn't broadcast the information to all the different computers. This isn't just good for speed. It is good for speed. It's a lot faster. But it also prevents a certain amount of security flaws because you can't see messages for other people. You can't send messages to everyone on the network very easily. And so switches are now the de facto standard. So now these days, obviously with them getting faster and faster, wireless networks are a lot more convenient as the technology has developed. I don't think anyone here is using the wired connection in this room. I use it in the other office because my wireless doesn't work up there. But wireless access networks, we discussed them a little bit already. We have a wireless router somewhere that handles connections for everyone, and you use effectively a two-way radio installed in your computer to make a connection to that wireless router, or access point as they're often referred to. The initial popular standard for wireless networking was 802.11b, which gave you 11 megabits per second. Was that right? Or was it 1 megabit per second? I can't remember. Slow. It gave you a slow connection, but a wireless connection, so you could walk around the house with it. Nowadays, G is more common. G gives you a much faster connection, and there's now the standard N, which allows you to use multiple antenna to get a much, much faster connection than G. But these are all very, very similar, and from the end user point of view, they are all just wireless connections. They're just a bit faster or a bit slower. But the typical way that it works is very similar. You just broadcast data over the air, and it's picked up by the wireless router, and then your connection is used. Now, the wireless router itself will typically connect via a cable to the local network. Now, the reason for this is that you use cables when you can. Cables tend to be faster, more reliable. This is why the infrastructure in this country is very good. We use the physical cables rather than using satellites or any other kind of connectivity. Wireless networking is very good for convenience, particularly at the end user state, but you don't want to be transmitting a lot of data over it because it's simply inefficient. Wide area networks, well, we've got our, this is better thought of actually as the mobile phone networks that we've got. Mobile phone networks are now becoming very, very fast indeed. You can effectively get broadband speeds on a good data connection these days. These transfer in very much the same way as this. Your phone, as it roams around the country, as you move around the city or around the country, will connect to local towers, radio towers that are set up or leased by your telecoms provider, T-Mobile, Virgin, BT, whoever, and that is what gives you the connection to the general phone service. What happens nowadays is that you also get a data connection that goes along with that, so you've got a much higher bandwidth for doing that. And there are some new technologies coming out that aim to give even faster speeds on that. 4G networks are about to come out, and we'll see sort of true broadband speed. It's becoming feasible for plenty of people not to have an internet service provider account through their telephone line. A lot of people are just having either a dedicated USB stick for mobile connections or just using their mobile phones. So the components that make up a typical home network are your DSL or your cable modem. This is the thing that you typically will plug into the wall that will handle it for you. This will connect to a local router. You use, which may be running particular services on it to protect the security of firewall that will protect unauthorized access to your network. network address translation. We'll get into that later. And then you may have wired connections to your local PCs if they're fixed and you have a wire set up there. And then you'll have your wireless access point that gives you access to your laptop as you roam around. So that's the edge of the network. That's sort of the edge of the network covered, the home access and home connections and mobile phone connections. Now we'll sort of move to looking at the core of the internet and the way that the internet works. Now the internet itself, as I've said, is a network of networks. It's a mesh of interconnected routers. Mesh not in the sense of mesh networking, as I was talking about before, but just computers that are multiply connected to each other. And what we're really going to look at here is how do we get data from one point to another on the internet, because it's really important to understand. Now, the traditional way that networks worked, that telegraphs and telephone networks worked, used an approach called circuit switching. These are the sort of key terms, circuit switching and packet switching. A circuit switching approach allocates a certain fixed chunk of network capacity to somebody using the network. This is the way that a phone line works. Now, if in the distant dim past, when you made a phone call, there would actually be a person sitting at the other end of the line, and you would dial your number, and they would take a physical cable and they would plug it from one point to another, and then you would have a circuit, you would have a virtual wire at the exchange point in the telephone network. So you would have a line that went from you to the exchange point would have physical wires that people would physically connect together, and then that would connect you to where you wanted to go. Now the disadvantage to that approach is that there are a fixed number of wires. You know, if you have 100 megabits of bandwidth and each fixed line takes up 10 megabits of bandwidth, you only get 10 connections, and then it's full, and the next person who comes along just has to wait until a circuit is freed. So the innovation that drove the whole networking architecture of the internet, it's pretty heavy stuff here, is the packet switching approach. The way that packet switching works is that rather than creating a fixed line between 2 points, it breaks up data into discrete chunks or packets and then sends those independently. And what this means is that you don't have to reserve a particular area of space. Everyone can just send all their data in the form of packets over one line, and the network can handle that, and you get sort of a variable amount of data going over it. So the advantages are that it allows more people to use the network. So I've already said this, but if you've got a 1 megabit link and each user needs 100 kilobits when they're active, and they're only active 10% of the time, then you only get 10 users. Yeah? So people use up the network bandwidth. But with packet switching, it becomes a lot more probabilistic. It becomes a lot more sort of based on contention and who's using it at a particular time. With 35 users, with the probability that more than 10 of them are active at the same time is less than 0.004%. So at any time there will be some bandwidth available for somebody, and so your internet connection might be faster, it might be slower, you might be sharing it with more people or less people, but more people can use this network, and in practice it's actually more efficient in general as well.
So by active, do we mean
sending data?
Actually making a request
Mhm.
or receiving, not just? Okay.
Yeah, sending or receiving data. So I mean the difference here is that in a circuit switched approach, if you dial somebody on the phone and you're speaking to them on the phone, you're using up data, you're transmitting data. But if you then just sit there and don't say anything, and they don't sit there and say anything, I mean, maybe it's a difficult phone call with a loved one, then you are using up bandwidth. You're using up 1/10 of the connection for your emotionally charged silence. If you do the same thing over a packet switch network, then other people can take advantage of your emotional state to transmit data. There's no love in the internet. So the approach that this, the impression that this gives is that packet switching is just better, and in the general case, that's probably not a bad statement to make. But it's not entirely true. It's not a silver bullet. Packet switching is great for bursty data. It's great for data that is slow sometimes, and then all of a sudden you need a lot of transmission. So say web browsing. Web browsing is quite a bursty transmission state. You need to get a web page and you want it to arrive now as quickly as possible, and then you might spend 20, 30 seconds, a minute reading it, 10 minutes reading it. The other thing that's simpler is that you don't need to set up the circuit. So when you set up a virtual circuit across a network, you actually need to construct the entire path. And so you have to wait for that path to be constructed, which probably doesn't take a great deal of time, but if it's happening for every website you want to connect to, then it's significant. But it causes certain problems in that packets can be delayed and packets can be lost. And so in order, rather than sending your data in one big stream, one big chunk across the internet that is protected and safe in its own little sort of encapsulated section, then packets get sent off sort of on their own into the network, and they find the best way across the network to where they need to go. And so the protocols that are, the data transmission, the protocols that are dealing with the data at either end, they need reliable data, and they need to be able to deal with things like network congestion if there's too much data being sent at a given time. So one of the sort of open research questions really in the internet, or one of the ongoing improvements in the internet, is how to get the nice aspects of circuit transfer, like a guaranteed amount of bandwidth or a guaranteed quality of service, whilst going over a packet switched network like the internet. How can you achieve that? You need this for things like audio and video. If you're streaming a video over the internet, if you're using Netflix or whatever it is, then you may want, if you're watching it in real time, if you're looking at YouTube, you kind of want a guaranteed amount of bandwidth to show you that video, because you don't want it stopping and starting and stopping and starting all the time. And this is particularly annoying if the reason that you're starting and stopping your video all the time is because of somebody who is browsing the web and could deal with a 1 second delay in the transfer, or a 50 millisecond delay in the transfer. So this quality of service idea, which pieces of traffic need a guaranteed amount of bandwidth and which ones can get away with a little bit of delay, is an open research problem. I mean, there's solutions, but not perfect solutions. I'm just thinking about, nearly at the end of the first hour, I'm thinking about, we'll have a break in 10 minutes, but I'll go over the networks themselves first. So the structure of the internet. We've talked about getting from the edge of the network, talked about the computers that occur at the edge of the network and how they connect to the internet, this big cloud in the center of lots of network diagrams. But these networks in the middle are sort of entities in themselves, and we need to know how they're structured. Now, the internet itself is hierarchical, as I've said. At the very core of the network, the very sort of big players, so you've got ISPs like Verizon, Sprint, AT&T, Cable and Wireless. These are what are called Tier 1 ISPs. These are the really, really big players in the international internet. And these provide global and national coverage for internet connections. And what they do is when they want to transfer data across each other's networks, so say you are somehow connected out here, but ultimately connected to this green network here. If you want to transfer data to somebody who is ultimately connected to the red network here, you're going to have to get your data from green to red and then to the person you want to reach. And what this requires is a connection between the networks, and this is what makes the internet work. Now, these links here are formed between the Tier 1 ISPs in what are called peering agreements. And peering agreements are one of the most important set of arrangements that make up the internet. For Tier 1 ISPs, because they're so big and they transfer so much data for so many people, there are generally free peering agreements between themselves. They agree to transfer data for each other for free, without charging for the network transmission, because it's a quid pro quo situation. They get the same response from other Tier 1 ISPs. And in fact, to some extent, the thing that defines a Tier 1 ISP is whether it can get free peering agreements with other people. There's no hard definition that says, if you've got this much bandwidth and this many computers and you're in this place, then you're a tier 1 ISP. It's more a case of when you are recognized as a tier 1 ISP by the other tier 1 ISPs, then you're a tier 1 ISP. So an example, this is just a sort of nice diagram of this kind of thing. What you get physically in this is a nice sort of link into the physical sort of geographical level of the internet, is you get what are called points of presence between the big ISPs. And what these are big buildings where the internet, the tier 1 ISPs physically route their cables and they physically make the connections between their networks. And there are a few of these around the place. I think there's 3 of them in London. That literally people build cables into them, and you have rooms where people sort of make the connection between these massive great networks and sort of link 2 large chunks of the internet together. And to some extent, particularly in the early internet, but it's still true nowadays, the way that these networks were linked, or the way that people agreed to make these to bring these networks together, were literally by the network operators getting to know each other and saying, right, let's peer our networks together. This was very informal. They were, obviously now for Verizon and Sprint, they don't have a guy somewhere that goes and meets another guy in the pub and says, let's peer our networks. But in the early days of the internet, when the networks were smaller and a lot more personally run, this kind of thing did happen. Now, obviously, the reason for this is that if everyone's peering in the same place, then you can peer to lots of other people. If you want to make a connection to another network and they're already with their cables there, then you can peer to lots of networks, and this does everyone a lot of good. Everyone can connect. So beyond the tier 1 ISPs, you have the tier 2 ISPs. Now, these are still big players. They're not, these are not tiny little operations. These are still things like the ISPs that you will be dealing with a lot of the time if you get an internet service provider connection in this country. So this might be somebody like Virgin or TalkTalk or somebody like that. Now, tier 2 ISPs don't have quite the weight or the power of the tier 1 ISPs, and so they pay the tier 1 ISPs for access to the network. They pay these tier 1 ISPs to carry their traffic, and then they charge other people to carry their traffic. So if you're connecting directly to a tier 2 ISP, then your service contract, the amount of money you pay them every month or every week, however often, is where they get their money, and then they spend some of that money on getting paid peering agreements with the tier 1 ISPs. So they're acting as middlemen. They may also privately peer with each other without going through a tier 1 ISP. These agreements can be paid or not paid, as far as I'm aware. So you can already see that this network is getting a little bit more complicated and a little bit more sort of interconnected, a little bit more mesh-like. And then at the final range, you've got the odd tier 3 ISPs, who tend to be sort of smaller players who will rent connectivity from either from the tier 2 ISPs or from the tier 1 ISPs directly, probably the tier 2 ISPs in general. And these are maybe local, smaller ISPs who you may deal with if you're not going with one of the big players in the market. I think maybe Zen Internet would be one of these in the UK, or Surf Anytime, or one of those little ones. Right, it's 12 o'clock. I would suggest that we have a 5 to 10 minute break, go and get a cup of tea, digest what I've said, and feel free to ask me any questions. Right, so we can get started again. There's a piece of paper for attendance passing around, so can everyone make sure that they sign that or tick that? Right, okay. So, back onto internet protocols here. So we've already mentioned that there's a variety of different protocols that regulate the behavior of communications on the internet. But this being the internet, things aren't quite that simple. There are a number of layers of protocols in order to handle different aspects of communications. You don't just wrap everything up into a big unified model of how everything works. Instead, what we have is what's called the Internet Protocol stack, and this is a slightly strange diagram of it. But what this gives you is an idea of the way that things run when you use the internet. So there are a set of protocols at the very highest layer, the application layer, and these are things like the HTTP, so email, World Wide Web, even phone connections are happening at the top level. And then when you use one of these services, at a lower layer, there are a set of protocols that define how that transport happens. So you've got SMTP is the email transport protocol. You've got the hypertext transfer protocol for web transactions, HTTP. And then below those that actually define the more sort of internet, the more sort of application level stuff, or the way that the particular form of communication you're using works, say email or web, you've got a more underlying protocol, which is the transport protocol. In practice, this is typically TCP, the transmission control protocol. There's also another one called UDP that we will talk a little bit about later, which is the user datagram protocol. But these are all layers. So firstly, it will be encoded with this set of protocols, and then it's encoded with this set of protocols, and then it's layered at a lower level into TCP or UDP, and then that is all thrown over IP, the Internet Protocol. This is the core of how the Internet works. And then below the layer of the Internet Protocol defines at a more or less basic level how the information is encoded for internet services to work. But then at a lower level, there are protocols that define how that gets pushed into the Ethernet, how that gets transferred over different kind of more physical links. And then all the way down at the bottom, you've literally got the physical transmission of what does a bit of information going over a copper wire look like? Is it what voltage? In practice, when you're transferring information over physical wires, certainly electronic information like that, it will be voltages going up and down. It will either be a high voltage to mean a 1 or a low voltage to mean a 0 in a binary protocol. And these things define, what's the high voltage, what's the low voltage, what pulses of light go over optic fiber, this kind of thing. So this protocol stack defines a series of layers, 7 layers, in what's called the OSI 7-layer model, that encapsulate your data in a variety of these protocols that allow them to transfer all the way from your computer through a variety of different systems, all the way down to physical wires that then transfer between computers and eventually get where you want to go. So to look at this encapsulation, the way that this encapsulation works here, the source, if you want to send a message, firstly you have it at the application layer, then that is wrapped up into a transport layer message, which defines how it's actually going to be transported. That's wrapped up into the network layer, which is obviously what's happening on the local network. The link layer defines it at an even lower level, and then the physical layer actually says, right, this is the sequence of pulses of light or high and low voltages that are going over this particular wire. And then that is what is actually transferred to, for example, in a local area network with Ethernet, to the local switch, where it is picked up at the link in the physical layer, transferred to a local router, and then goes over networks. And what you can see is these protocols kind of being layered onto the original message, and then being peeled off as required, and then relayered on as required until they eventually get to their destination. So it's not really necessary to understand at this point the sort of variety of different layers of the protocol stack. But what you should get out of this is this idea that the message does not just transfer raw across the internet. First it's layered in a certain type of transport, and then it's transformed or layered in other types of transports, and then moved all the way across the net. So, this will be in the exam. No. This is the, in some senses, this is the core of the internet. This is the IP datagram. This defines the sequences of data that all go together to transfer information across the internet. The IP protocol. I'm not going to go through all of these because there's a lot of information there. But particularly important in this situation is the IP protocol version. Now, most of the internet at this point is running over what's called IP version 4. IP version 4 has been around for a very long time. It's one of the things that defines how big this data is. Is everyone familiar with bits and bytes and what that all means? If there anyone isn't, then please put your hand up and I won't shout at you, I'll just explain it. Okay, okay, wonderful. Bits and bytes are how computers store and transfer information. Ones and zeros. It's the simplest way of representing numbers. We have a decimal number system where we can represent numbers from 1 to 10. Instead of doing that, you can represent numbers with strings of ones and zeros. So this is how computers store information, because it's very simple, it's very basic, it's the most abstract way of storing information, more or less. It's also, as I've said, it can be represented very easily as a high voltage or a low voltage. So when you store information on a computer's hard drive, what the hard drive is actually storing is say a traditional hard drive has a magnetic platter, and it writes onto it high and low voltages in very specific locations. And when it wants to read the information off it, it looks at it and detects the voltage and finds out how that information is stored. So, as with any number, the longer the number, the larger it can be. So a 32-bit number is longer than a 16-bit number. It can store more information, it can store more details. Computers store everything as numbers, effectively. So when you're thinking about typing something on your computer, the letter is actually translated into a numerical code that the computer can then process. When it displays information on your screen, what it is actually doing is writing particular numbers to that cause particular pixels on your screen to be red or green or blue or any other colour. So everything in your computer is ones and zeros. If you open it up and shake it out, a load of ones and zeros come. So currently the IP protocol version 4 defines a certain identifier. Let's have a look. The IP address, this is something I'm just going to cover briefly here. The IP address is the number. You can think of it like the phone number that a particular computer has on the internet. It's a more or less unique number, and if a computer knows that number, it can find that other computer on the internet. So we tend to represent these numbers as 4 segments of numbers from 0 to 255. So it'll be something like 82.68.72.253. This is how we write IP addresses. When we use the internet, we typically have a translation into human readable names using something called the domain name system that I think will be covered in other lectures. But when you type google.com into your browser, what actually happens is that your computer goes and says, well, what is google.com? What number is google.com? And the DNS server, the sort of authority that knows these things, will then tell that computer, oh, google.com is something that I can't see at the moment. Let's have a look. I can find it if you want. There you go. Ping google.com. There you go. Google is 173.194.41.69 in this particular case. And so that can be used to route information around the internet. Now, one of the problems with IP version 4 is that the 32-bit source IP address only gives a certain amount of space for the number of computers on the internet. Now, when it was designed, there were a few thousand computers on the internet. Now there are more than a few thousand computers on the internet. There are more than a few million computers on the internet. In fact, I believe there are more than a few billion computers on the internet, if you include mobile phones, routers, and all the other devices that are now being connected. So one of the key elements of the new version of the IP protocol, IP version 6, don't ask why there isn't an IP version 5. It's a long story. Is extending this range very greatly. So the current idea is that in an IP version 6 protocol, there's a much greater space for addresses. And roughly speaking, everyone in the world could have an allocation of a number of IP addresses equivalent to the current internet. and still have plenty of space left. So the idea is that in IP version 6 we will never run out of space. In computer science, if anyone ever says we will never run out of space, call them a liar. Obviously, Bill Gates very famously once said, nobody will ever need more than 650 kilobytes of RAM. If there's anyone in this room with less than a gigabyte of RAM on their computer, I would be very surprised. So I'm sure we will find some way to waste all of the address space in IP version 6. But for the moment, it's very good. It's been very difficult to change from IP version 4 to IP version 6. And the reason for this is that it's relatively low in the protocol stack. Now what that means is that everyone agrees on it, and it sits at a couple of very important places in the internet transfer. And the trouble is, if you change this and everyone hasn't agreed, then you can actually break the internet, for want of a better word. Or rather, you will break small parts of the internet. If you start transferring stuff using IP version 6, and the person that you're transferring to, or a computer on the path to the person that you want to speak to, is not using IP version 6, then it all breaks and it all goes wrong. So there's been a very long procedure of trying to change from IP version 4 to IP version 6. We're getting there, but we're getting there because we're actually physically running out of IP version 4 numbers. And it's only that sort of impending Armageddon of not having any more IP addresses to use that is causing us to switch. Yeah.
I'm curious if, at a very high level, could you explain how that transition happens and how you?
What, from IP version 4 to IP version 6? So first, the standard has to be agreed. IP version 6 has to be developed, and the trouble is, again, what happens at this point is it's not just because IP version 4 is running out of addresses. That's probably the driving factor at this point, because it's an actual impending serious problem. But there are other little flaws. You know, IP version 4 was designed maybe 30 years ago I'm not sure exactly when it became IP version 4, but sort of 30 years ago for a very early equivalent of what we now call the internet. And it's a real testament to how amazingly good these designs are, both the TCP, the transmission control protocol, and the internet protocol that make up the core of the internet. It's a real testament to how good they are, that they're still handling the internet now. But obviously, when you start talking about IP version 6, everyone says, oh, but we want to put security and privacy in it as well, and mesh networking, and this and this. So first thing you have to do is to crush everyone's enthusiasm and come up with something that is actually sort of sensible and will work. So that's a very long process headed by the IETF, the Internet Engineering Task Force. Then what you have to do is you have to start writing the software. You have to start actually producing equivalent services to the current services that work over IP version 6. So for example, you know, your web browser at the moment, let's assume your web browser doesn't support IP version 6 in that sense, but say if your computer is trying to find another computer on the internet and it only knows how to speak IP version 4, then if everyone suddenly switches to IP version 6, you don't know how to find anyone anymore. So the reason this is such a problem is that you have to change the core routers of the internet to start supporting IP version 6. So people don't like to touch things in the core of the internet for very good reasons, because if you do something wrong, then you can break very expensive things. So what happens is you get a lot of technical people from all over the world who discuss it on mailing lists. There is a particular mailing list called the North American Network Operators Group mailing list, called NANOG, which was one of the first big discussion forums for network operators, the people that actually functionally keep networks working. And we're talking about the large-scale internet networks here, tier 1 ISPs and things like that. And they come up with a plan to say, we need these services to support IP version 6 by this particular date. And then they start very gently testing, you know, can we make this service run? Is it running? Now, to some extent, it's quite easy to run a service in parallel, because what you do is you enable IP version 6. You say IP version 6 is something that we're now going to support, but then you aren't going to get many people using it through your network. So you can usually do some testing like that. And then but you need to interact with other people who are doing it, and you need to load test it. You need to say, you know, is this working on my one PC? But then when I turn it on for the whole internet, the internet just breaks and we all go back to living in caves. So that happens, and then you just increasingly get people testing it, switching it on, starting to use it between their particular networks. About maybe 6 months ago, there was IP version 6 day, where a lot of large services turned on the IP version 6 version of their services. So Google enabled IP version 6 for their networks and their services and things like that. And that allowed people to test, see what broke, see what went wrong. But there isn't a sort of simple answer to your question. It's very organic, it's very messy, it's very... And there are lots of details that I don't know because I'm not really in that core network operator group thing.
Just to build on that,
Yeah.
why is it that the ICANN has the ultimate authority on assigning IP
Well-
addresses?
So we'll get into that a little bit here. I will mention it somewhat, but wait for the history and development of the internet lecture for that one. I won't say anything about it now. I'll wait until we get to the end. Sorry. Yes.
Yeah, I just have a question
Yeah.
about these two versions of IP protocols.
Yeah.
So are you saying that the next sixth version will include all the addresses that already exist and replace the older version entirely, or they will coexist?
So there is an effort towards making it backwards compatible to some extent, but the way that the internet addresses are actually used is different. So, for example, this here is a 32-bit IP address, which means that it is expecting 32 ones or zeros to define the number.
Yeah.
In the IP version 6 protocol, it is 120. I think it's 128 actually. I'm going to admit my ignorance there. I'm not sure if anyone wants to correct me on that. Which means that it will expect 128 ones and zeros. So 32 bits won't work there, but I think there are translation mechanisms that allow you to put, you know.
You can just put zeros.
Yeah, well, it won't be quite like that, but there'll be something along those lines. Yeah, but I mean, just to give people, because one of the things that not many people will actually be that familiar with binary, but one thing that's worth noting here is that 32-bit gives you 2 to the power 32 numbers. 33-bit is therefore twice the size. 34-bit is twice the size again. 35-bit is twice the size again. So when we start talking about we start talking about 128, you can start to get a feeling of the scale of the increase in the numbers that we're talking about here. It's like that story about the rice grain on the chessboard. Is that something in a story that people don't know? There's a legend about a king who he asks somebody to perform a service for him and says, "Oh, you can have all the gold you want." And the person says, "Oh, I don't want any gold, but what I want you to do is put 1 grain of rice on the first square of a chessboard, and then 2 on the second square, and then 4 on the third square, and then 8 on the." And the king says, "Oh, no problem at all. You just want a bag of rice." And then obviously by the time he gets to about the 16th square, then that's all the rice in the world. And I think the king chops his head off.
Excuse me. Just out of curiosity, is there some kind of preliminary agreement on just what an IPv6 address will look like? Will it be hexadecimal or?
Yes, it's hex. And in general, obviously it's a question of presentation.
Right.
But you can write them any way you like. But
like
I think as far as I'm aware, then they come in chunks of hexadecimals.
Right.
And I've just been verified there are 128 bits in the IP version 6 header. So there are also this also we can mention now a couple of other things that people have added in. One of them is priority. Now this is quite interesting and in some ways controversial, which is we were talking earlier about how if you've got a video or you're talking on Skype, you want your data to be prioritized over other types of data. Now, in the IP version 6 header, there is a priority section that allows you to request that this data will be given higher priority. Obviously, there's no guarantee. You can't demand it because it's down to the individual routers that are transferring your data, but it exists. flow label identified datagrams. Datagrams are the little packets we were just looking at in the same flow, although apparently the concept of flow isn't very well defined. So you can use this header to say that these datagrams are within the same something that will probably evolve as people start to use the protocol more and more. I think the idea here is to say that that this is part of the same transmission, this is part of the same Skype conversation as that one. Let's just skip that. So we went a bit deep there, but we're going to sort of zip back up a bit. So I'm going to repeat this phrase again. A network of networks. We've got all these different ISPs. We've got the local ISPs, tier 3s, tier 2s, tier 1s. And when you send a packet of data, when this packet of data is transmitted across the internet, it travels across a lot of these networks. And that's really the key of how the internet works. If you wanted the internet in one diagram, then that's it. So we're going to talk a little bit more now about some of the technical issues that come out of the internet. We've seen how the internet works to some extent at a lower level, but we're going to have a look at some of the more real-world problems. Loss and delay of packets. So we've already said that one of the disadvantages to packet switch networks is that you get packet loss and packet delay. When you are transferring packets and it goes to a router, the router has a certain capacity. It can handle a certain number of packets in a certain amount of time. If you get too many packets in that period of time, you have to queue them. You put them into a buffer inside your router, and then that packet has to wait until it gets its turn to be transmitted. Obviously, if somebody's relying on that packet to arrive quickly, then this can cause a delay, and this propagates up the chain of protocols until you get a skip in your YouTube video or a dropout in your Skype conversation. This little bit here, the queue, is the source of an entire field of study called queuing theory, about how is the best way to do, obviously not just in this case, but the best way to queue data. Or in fact, one of the examples that they use a lot is when you're in the supermarket and there's a whole load of queues. What is the best way to get all the people through as efficiently and quickly as possible? And there are lots of sort of slightly counterintuitive results, like the fact that if you've got a lot of shopping, it's better for everyone if you let people with not much shopping go in front of you. But it's also about how many tills do you have, how long do you let the queues get, and things like that. But it's a very sort of very mathematical, very interesting field of study. But in the real world, what do these delays really look like? Well, there is a program. There are a certain number of very sort of key programs on the internet, sort of applications that you can run on your PC that are very sort of low level and tell you lots of things about how the internet works. You saw me run one of them a couple of seconds ago when I pinged Google. Now, ping just sends a message to a remote computer and says, "Are you there? Are you alive?" And if they are, then they say, "Yes, I'm alive." It's called a ping. Another one of these core programs that has been around for a very, very long time is called traceroute, that looks at the entire route of communication across the internet, and from the source which is you to the destination that you request, and it says where are my packets going, and how long are they taking to get there. So what it does is it sends some data, and it uses a couple of tricks in the way that IP works in order to cause the packet to die en route effectively. So one of the things that we saw in the IP datagram is the time to live field. Now, time to live says not a chronological time, but how many hops, how many more computers can I go through before I assume that I've just spent too long doing it? And every time this IP packet goes from one computer to another, the time to live is decreased. And when it's finally decreased, then the packet is dropped and a notification is sent to the source.
Could you please repeat what is time to live?
Time to live is the number of computers that the packet can pass through before it just dies. So you can use this to control how far your packet gets on the internet. If you set time to live to 1, for example, it will get to the first computer on the route and then just not go any further. Where have we gone? Where have we gone? Where have we gone? So what traceroute does is it sets the time to live for a given packet to an amount that will cause it to drop out at certain points on the route, and then it measures how long it takes before it gets a response that that packet has died. And the result of this is that it gets a response from every computer along the route from the source to the destination, and a timing for that. And let's see if I can give you an example. If I can give you a, you probably can't read that text actually, but let's have a look. Trace routes. Oh, actually, can I see it? Let's go to my remote server. Oh, go to my remote server. Right. So, if we trace route to, I don't know, Baidu.cn, so that we get a nice route to China. Hopefully, what my remote server will do. Oh, cannot handle host command line argument. Let's see. Oh. Never show people a live demo in a let's just try google.com. Right, yeah, no, it's because the terminal's not working properly. So here we go. It's gone from my computer, which is running at a hosting provider called oneandone.net, and it said, so the first place I go to is a oneandone.net computer, obviously handling the local computers, and then it's moved through a few of their other computers on their network first. It's gone from my computer, which is sitting somewhere, I can't remember exactly where it is. It might be Sweden, but it's gone to a computer in their network, which has passed it to another computer in their network, which has passed it to another computer in their network, which has passed it to another computer that we couldn't see, another computer that didn't send us a response. We know it's there, but it didn't give us a response that allowed us to identify it.
Is it number 5?
Yeah, number 5. This is why we've got these little stars here. I'm sorry for the people at the back that probably can't see this. But then from there, it's passed it off to another computer on the internet. This is probably one of the routers because it doesn't have a usable human-readable host name, which has then passed it to another computer on the network, and it's eventually taken me to FRA07S07 in F102.1E100.net. 1E100.net is Google's name for its internal services, because Google, before it was the name of an internet service provider, means 1 to the power 100. 10 to the power 100. And so all their internal services that don't face the user are called 1E100.net. So when my computer tried to get to Google, it went through this entire series of computers before it finally got to a Google server that was willing to talk to it. Right. Where's my slide gone? Come back. There we go. Okay. So, TCP and UDP. I've mentioned TCP. I'm going to talk about it a little bit more in the next couple of slides. But UDP it's called the User Datagram Protocol. And what it is it's a very, very stripped down, bare bones version of an Internet Transport Protocol. It's a best effort service. We talked about this right at the start of the lecture. It doesn't say, I'm going to guarantee this data will get there. It doesn't say, I'm going to get it there in this order. It doesn't say anything about how long it will take to get there. It just says, I'm going to send this data, and if it gets there, then that's great. So segments can be lost en route, and you'll never learn about whether they were lost. It doesn't send you any notification that things were lost. And they can be delivered in a different order to the order that you sent them. It doesn't have any kind of setup. There's no handshake. It just sends data to a remote computer. If that computer doesn't want to see it, then the computer just ignores it. If the computer isn't ready to deal with that particular type of data at that time, then that's just unfortunate. UDP really is just it's a fire and forget. I'm sending some data to somebody. So you might say, why does this thing exist at all when we can do better? Well, one of the advantages is that, for a start, there's no connection, which means that it's fast. When you set up a connection, you have to send a message to the computer, you have to wait for the response, and then you can send data. With UDP, you don't need to wait to do that, which, as you've seen, it can take a second or two to get data across the internet. If you're doing something very, very fast, you don't want to have to go through this process. It's very simple. There's nothing that the computer needs to store. It doesn't need to keep track of what data is happening in what order. It just says, go, send the data. It's small, and also there's no congestion control in UDP. Other types of protocol will say, don't send any more data, you've sent too much data, we'll wait a bit, calm down, we'll wait a bit, and then you can send some more data in a minute. UDP just says, fine, let it go. UDP is very useful for services that want fast delivery and don't care if you lose a little bit of the data. Skype uses UDP for its transport of its voice communication. So if you're talking over Skype and you get a few skips and a few jumps, then that's because the UDP packets are being lost in transmission. It gives it the ability to be as fast as possible, and it can afford to lose a bit of quality. But the one that really underlies the internet, the thing that really, on top of the internet protocol itself, is the transmission control protocol. Now, what the transmission control protocol gives us is reliable delivery of data in the order that we wanted it to be delivered. It's point to point, so there's one person sending and one person receiving data in a TCP connection. And what you get at the other end is a stream of data that matches the stream of data that you send. So you don't get data sort of chopped up into messages that you have to reassemble. It comes out of the TCP protocol anyway as a stream of data. It's got various different sort of tweakable elements in it that allow you to control for congestion of the network, for it to say, look, there's too much data being sent, your data's not going to get through in a reasonable amount of time, so slow down. And it also buffers at the sender and receiver side. So if you send some data and the receiver isn't ready to process it, then it will buffer it, whereas UDP would have just thrown it away. You can build TCP on top of UDP if you're perverse like that. You can get some of these properties, and this is another reason why UDP can be useful, is that you can send data in UDP and you can arrange for it to do some of the things that TCP does. So UDP is a bit of a Swiss Army knife, whereas transmission control protocol is your sort of reliable way to transfer data. And nearly everything that you run into on the internet, web traffic, email traffic, even Skype's setup before it starts the actual voice call is done over TCP because they need that reliable.
What does the pipeline mean?
Pipelined. It means I don't know how to sort of. What's a good way to it basically means that it's sort of it's wrapped up in something that will look after it. I don't even know how to. It's such a sort of internal word to me that I don't even know how to sort of explain it. But pipelining is relating to this kind of stuff. It kind of gives it, control of the data. It will let it go through safely and securely, and secure in the sense of arriving. Sorry if that's not a good answer.
Oh, that. I understand.
So other things about the transmission control protocol is it allows you to send data in both directions in one particular connection. So this means that you can have a two-way conversation going on at a particular time. So in contrast to UDP, one of the things we said was an advantage of UDP was that it's not, it doesn't require a setup phase, whereas TCP explicitly does. It's connection oriented. You make a TCP connection, and then both computers are aware that this particular connection is going on, and they can use that to track the data that is going through it, to make sure it arrives safely, to make sure it arrives when you want it.
So what orders of magnitude are we talking about in terms of loss, I guess, difference between UDP and TCP?
It really depends on network conditions. It really depends. And there are at lower levels of the protocol stack, there are reliability elements that you don't just lose data. Well, you do lose data randomly in UDP, but there are lower levels do make efforts to ensure the best possible delivery. But what they don't do is what TCP explicitly does is it says, if this packet is lost or damaged, I know where it was supposed to be in the stream, and I can request it again. So you can actually guarantee, if something arrives mangled or doesn't arrive at all, then you can detect that and you can get it and you can reconstruct it. And the sender will send it again, and the receiver will acknowledge that they've received it this time. And so this can cause delays, but it means you've got sort of proper reliability. But I can't tell you off the top of my head because there's such a variability in depending on the network, depending on the distance travelled, things like that.
How does it do it? Is it through a checksum?
The details of the TCP, it has a variety of mechanisms. One of them is simply the sequence header, which is this packet is number 25 in the connection. So if you see packet 27 in the connection, you haven't seen packet 26 in the connection, you know something's wrong, or after a given time you know that something's wrong, and you can say, can you please resend me packet 26, segment 26 in the connection. But there's a variety of ways it does it. But I mean, the standard thing that happens, or the first thing that you see in a transmission control protocol is a data packet that says SYN, S-Y-N, synchronize. And then you get an ACK back, acknowledge. I acknowledge that you want to make a connection. And then you send back SYN ACK, which is like a combination of the two to say that we have now got a TCP connection open, and then you can start getting this reliable stuff over the top. And there's all sorts of little tips and tricks for how it does that.
So how big is the TCP packet? Or is it variable?
I don't know off the top of my head, actually. I think it's I don't know what the overhead of TCP is, not off the top of my head. I'm sure you could find it on Google very easily. It's not a huge amount. It's not a huge amount. It exists, but it's not a huge amount.
It was on one of the other slides.
No, I think that was IP.
Oh, IP.
That was the IP overhead. Okay, so we've talked a little bit about how the fact we're running out of IP addresses. But even before we started actively running out of IP addresses, we didn't necessarily want every computer that was connected to the internet to need its own internet address, its own IP address. If you were running a large organization, you maybe just wanted to, you maybe have a certain allocation, you've bought a certain number of IP addresses from the people that distribute these things, and you don't want to waste them on a computer that never really needs to be reachable on the internet. Specifically, a web server needs an IP address because people are going to connect to it from all over the internet. But the computers that you're using right now don't necessarily need specific IP addresses so that people can get to them. So one of the ways that this was resolved, or one of the schemes that is quite widely used, particularly in home networks and to some extent business networks, is what's called network address translation. And what this does is it gives the router, the sort of link between the organization and the rest of the internet, has a particular IP address. It has a normal internet IP address. Behind that router, on the local network, the computers all have internal IP addresses. Now, there are specific IP addresses that are designed never to go over the internet. These are examples of them. Any address that is 10.0.0.1 will not go over the internet. It's designed for just local use on local networks. There's also anything that starts 192.168 anything can go over the internet. Cannot go over the internet. So what happens in this approach is that this means you can have 1,000 computers behind your, in your internal network behind your router, and you only need one IP address facing the internet to let them connect to the internet. And what they do is they send their requests to the router. The router then reassigns them its own IP address and keeps track of which computer that packet came from and where it's supposed to go, and then it sends it off to the internet. When the response comes back to here, but the router has taken note of the particular connection that we're interested in, and it sends it off to the internal computer. Now, the disadvantage of this approach is that nobody from the rest of the internet can directly get to these computers. They can't start a connection to them. They can only respond to a connection, and they can never see the specific computer. So if one of these is a web server and one of these is an evil hacker, then the evil hacker will appear to be this computer, as opposed to being sort of specifically identified. Now, it could well be that this router will know exactly which one it is, but the specific point is that this allows one computer to act as many computers, to act as a channel for many computers.
So is this kind of how proxies work?
It's very similar to how it is a type of proxying, but it's a kind of total proxying. Like, when people talk about proxies, generally they're usually or often talking about a web proxy that just handles your web connection for you. But the same applies in that situation. Tools like Tor that we mentioned earlier, they will proxy a number of different types of connections for other people, and VPNs are another way of doing this kind of thing. So this is a particular problem for Skype, because Skype, as we've said, uses UDP to connect directly. It uses peer-to-peer mechanisms to connect directly between computers. So there is a problem with people who are behind a NAT using a service like Skype, or indeed many other services like it. And to be honest, the details of this aren't necessarily something we need to go into, but basically what happens is that that computer connects to a relay that is run by Skype. This is why we use TCP to set up the Skype connection. And what that does is that sets up all the parameters necessary. This relay then calls the other person that you want to call on Skype, and their computer then uses the relay to establish a connection through the NAT router, and it can then cause it to connect directly. But this is more to illustrate the fact that there are problems if you are behind a NAT. This causes problems for local computers. If you look in the advanced preferences of a number of services like Skype, there's often a tick box that says tick here if you're behind a NAT or a firewall, and then it will do extra things to make sure that the connection can be established around it. So final stretch. Generally speaking, the connections on the internet are what we call are point-to-point. They're single connections between one computer and another computer. In general networking, an alternative approach is multicast routing, whereby one computer can send messages to a number of computers simultaneously. It's a broadcast, but it's called multicast to many computers. Again, this is more of just an illustration of a problem in networking that does become significant in large networks, where the means by which you determine how to get messages to multiple other computers needs to be resolved. Actually, I think I'm not going to go into multicast routing because we've only got 7 minutes left. But what I'm going to finish just with is quality of service on the internet, because we've spoken a lot about getting stuff to other people as quickly as possible and how we could maybe preferentially treat Skype or video. One of the most sort of popular current ways of doing this is through a process called diffserv, which is a quality of service mechanism for traffic on the internet. And what it allows is basically, almost like we saw in IP version 6, it allows certain classes of traffic, which can be identified by the routers, to be treated preferentially because of their nature, because of the type of traffic they are. So what can happen is that a router can identify that we are dealing with Skype traffic, with voice over IP traffic that needs to get there quickly but isn't going to use a lot of bandwidth. And it can bump that up in the queue. It can pass it more quickly than other traffic that can perhaps tolerate the delay or will require more bandwidth but deal with lag. Now, the way that diffserv works specifically is based on the class of traffic. It identifies this is a Skype conversation, this is a YouTube video, that kind of information. And on the basis of that class, it marks traffic as being prioritized or not prioritized for the specific hop that it's dealing with at that point, the specific transmission from that computer to the next one in the route. It doesn't enforce it for anyone else. It doesn't provide any guarantees. It just says, I will preferentially treat this traffic for this particular hop. One of the earlier ways to do this was something called int-serve. Or maybe I should say one of the alternative ways of doing this, which uses a similar idea that you're going to give quality of service by prioritizing traffic. But the way that this works is for individual applications as opposed to classes of traffic. So this is something that is handled by the application. It says, I am a particularly priority needing type of traffic, so please transfer this particular connection faster than the others. And then the int-serve servers determine, the servers that support int-serve determine whether to honour that request or not. So the difference here is that this is somewhat fine-grained way of doing it. You know, each individual application can request a prioritised channel through the network. But the downside of that is that in setting up this prioritized channel, you need every computer on the path, every router through which you're going to travel to support the architecture and to agree with you that you are a prioritized type of traffic. So diff-serve is how this is sort of practically achieved in networks, whereas int-serve is an alternative that hasn't seen as much adoption. So, to summarize. We've had an overview of the internet. We've seen the setup, the way it works. We've talked about the nature of protocols, their fundamental role in the internet and how it works. We've looked at the physical structure of the internet and the logical structure of the internet in terms of the network edge, the hosts, the computers that live at the edge of the network, the core computers, the routers that transfer huge amounts of traffic across the tier 1, tier 2 ISPs, the various networks that make up the internet. And we've also looked a little bit about how you actually get that connection to the internet in the first place. We've gone over the differences between packet switching and circuit switching, the fact that the internet largely or almost entirely uses packet switching versus the earlier model of circuit switching and internet structure we've already said. We've looked at the concept of performance, the loss of packets, the delay that can be imposed on packets, and also things like bandwidth and lag. We've looked at the layering and service models. We've looked at the protocol stack that says this is handled at this layer of the protocol stack, this is handled at this layer of the protocol stack. We've looked at network address translation, NATs, that can allow you to have a local network which doesn't have public IP addresses exposed and allows multiple computers to share the same IP address to some extent. And then we've had a very brief look at quality of service approaches in the network. And we have 3 minutes left if you want to ask me any questions.
Is there potential for this prioritizing architecture to sort of become very political? I guess
Okay.
if you're potentially sort of privileging someone's Skype conversation over
Right.
someone accessing.
So one of the big sort of political regulatory topics on the internet, particularly at the moment, is called net neutrality, network neutrality. It's a very misunderstood term. It's a very easily misunderstood term. The idea of net neutrality, or the principle of net neutrality that a lot of people try to uphold, and other people completely disagree with it and just want it to change, is that you should not prioritize any traffic over any other traffic based on who it's coming from whom it is coming. So the idea here is that you shouldn't be able to have, say, a tier 1 ISP enter into a specific agreement with another tier 1 ISP to say, I'm going to treat your data with higher priority than this person's data because you paid me a lot of money. The idea is that at the core of the internet, and to some extent sort of slightly more on the edges of the internet, data is transferred agnostically of who the source is. And to some extent, that is how it occurs at the moment. Now, the political issue there becomes, some people will say, well, we should have a free and open market if we want, if this would improve the services, because if people are willing to pay for faster bandwidth, they should be allowed to do that. We should be able to have, the invisible hand of the market will prop up our internet for us, and we can get faster data connections. It will promote faster data connections. But what network neutrality doesn't say is that you should not prioritize types of traffic over other types of traffic. So this is the quality of service approach. So Skype needs low latency, not a huge amount of bandwidth, but you know, a reasonable chunk of bandwidth, but it's critical that it gets there quickly. To take that traffic and prioritize it for those particular purposes is within net neutrality, and is the sort of thing that tries to avoid the political debates and the regulatory debates. When you start talking about prioritizing Verizon's traffic over AT&T's traffic, or BT starting to prioritize somebody's traffic, or to charge Google because they run YouTube, who transfer a lot of data over BT's network, then you start to get into a very messy debate as to what would be the effect of this on the internet. Net neutrality, I'm a supporter of net neutrality, and I believe that the majority of network engineers are, but there is a not insignificant group of people who say that actually we should open this up to a more sort of free market approach. So that's the difference here is between quality of service based on service as opposed to quality of service based on customer.
Yes, but I mean the quality of service can also be used to kind of achieve political goals, because in Germany, for sometimes, they try to slow down peer-to-peer connections.
Yes.
So
yes. Yeah. No. That's so. This is something. Okay. Yes. This is. I think So the key, I would say, here is in motivation. If you are doing it for quality of service purposes, then there isn't a general belief on this topic. There are lots of debated opinions, but one of the opinions is that if you're doing something for quality of service purposes, to improve a particular, the overall running of your network, then you are perfectly at liberty to say, shut. What's the word? Set off, 60% of your network for BitTorrent traffic, and then if it goes over that, then BitTorrent starts to get degraded, so that you've still got enough room for Skype and web and email. But if you do it because you don't want people to be file sharing because of copyright reasons, or if you do it to HTTPS connections because you don't want people using encrypted websites, so this is something that's happened in various countries around the world, is that they haven't blocked encrypted access to websites. They've made it sufficiently slow that nobody bothers. These kind of approaches are something that a lot of people have problems with.
So net neutrality is really sort of a utilitarian sort of approach, the greatest good for the greatest.
Yeah, there's a lot of that in the internet. Particularly people like the IETF, and there's a lot of engineers in there, and a lot of the engineers like to have this approach that we don't make political decisions, we make engineering decisions. This is a not stated quite like that, but this is almost a mantra that you hear, is that we do engineering, not politics. Now, I'm not sure that that's possible. I'm pretty sure it's not possible, actually, but particularly because if you want to get into it, a good number of the engineering decisions could actually be sort of construed as representing a particular type of political ideology, the sort of San Francisco libertarian ideology thing, which isn't necessarily a bad thing if they do make good engineering decisions. But yes, that is the approach I would say. But like I say, net neutrality is such an open term that lots of people have lots of different interpretations of it, and you could quite easily find somebody who has a completely different opinion to you. But I think the good thing to overcome is this idea that some people have when they first hear it, that net neutrality means you treat every packet of data exactly the same, and it doesn't matter what it's doing or what's happened with it. Everything is neutral. That's not what net neutrality, generally speaking, means. So, yeah. Okay. Right. Well, thank you very much.